Those who are online, can they tell us if the audio is good? And one of you get a thumbs up. So, what are we going to do today? As I said, the meters are in the front. What are some things that I want to discuss? The conceptual questions, I think most of you answered them well. There was the question that asks you to compare deterministic and probabilistic seismic hazard analysis. Yeah, problem 3, question A. I'm sorry. So here, what are the assumptions about the probabilistic and deterministic hazard analysis? The main thing, like, it's not so much what you're like. So, can someone try to answer this question again? What are the assumptions when we in the deterministic analysis? What do we need to decide in order to come up with appropriate design route motions? Yes.
The epsilon or the percentile.
The epsilon, yes, the epsilon and the percentile for the ground motion. So that's given a scenario where in the distribution we're going to sample the ground motion from, and then the scenarios themselves, right? So that should tell you that this is not the like. I think some of you wrote that like don't remember now exactly, but that the deterministic analysis gave like the upper limit for the ground motion. That's not true, and that's something that is important to recognize that it's not true. So part of the deterministic analysis is choosing the percentile of the ground motion, and for that to be the upper limit, that percentile should be 1, or the epsilon should be infinity. And in this case, because we're using unbounded distributions, that should be infinite. So, like, very quickly, like, given some scenario, we have the ground motion probability density function following a log normal distribution that looks like this. So this upper tail, although in terms of, so this is f of the same. And this is the value of the spectral acceleration. So the upper percentile, like the probability of exceedance of 1 would essentially require you to integrate the area of the distribution until you have until you reach one, and that should be the ground motion value. That will only going to happen at infinity. So none of these methods gives you sort of a conservative or upper limit for the ground motion that you should expect. Both of them are trying to come up with reasonable values given the seismicity of your region and the importance of the structure. And the key difference between the two is essentially the level of simplicity. In the probabilistic, you are going to say all possible scenarios. We will consider all possible scenarios, and then from them evaluate which is the most important and come up with a design ground motion values based on that. In the deterministic, from these thousands or tens of thousands of scenarios, you're going to say, okay, these are the most likely, subjectively, the most important, and then only do the calculation using that. Is this clear? That primarily that neither of these methods providing an overall conservative limit, or are there still any questions as to why this is the case? Okay. Maybe we can briefly cover this as well. So as a reminder, which can remind me what are the definitions for the different distance metrics? And even those online, if you want to unmute yourself, please do, or if you want to raise your hand and then write inside. So what is RRAP? How do we define it?
Radius of rupture. I don't remember what the thing is, but it's like the X distance, the Y distance. I mean, the X distance, the Y distance.
This is so what you said is like the Euclidean distance, right? If you are in a Cartesian system and your space is defined like if you are in 3D space, the distance between 2 points is the horizontal, like the two horizontal plus the vertical distance squared and the squared. But it's the distance between distances by definition a distance between 2 points. So one point is the side, right? That we will measure the distance from. What is the other point between which we are going to calculate the distance?
The top of the
Why is it really the top of the rupture? In some cases, it happens that it is the top of the rupture, but not always. Yes, please.
It's the shortest distance.
The shortest distance. So for this station, it will be the distance between the site and which point on the rupture? The top of the rupture, I'll be correctly saying. But for this, it's point to point. For this point, this distance. For this distance, which it will be the distance between this point and which point on the rupture? What is the shortest distance between a plane and some point? The node, right? So it will be this distance, where like the angle between the rupture plane and the line that this distance lies on is 90 degrees. So how can we easily calculate that distance? what is this angle? So this is 90 degrees, we agree, right? What is this angle or this angle? What is the angle of the fault plane?
45.
45. So then this is 45, right? What then does that angle should be as well? 45. So it's an isosceles normal triangle. And what do we know for isosceles triangles? That the two sides have equal length. And if you combine that with Pythagoras theorem, we have, like if we call this RR, this distance will also be RR. So we have RR squared plus RR squared is equal to what? What is the hypotenuse here? This is like smooth geometry. You don't need to tell me the number exactly. Here we have this side squared plus this side squared should be equal to what side squared? This one, right? So that should be in our case. So, and it should be equal to this side. And we know the coordinate for this triangle. So this is at 13.5. So this is equal to 13.5 squared. And then you can quickly do the math, and you have R up is 1 over square root of 13.5. Is this clear?
Just from my own understanding, is the angle that, say, like our rupture makes with the thing, it's not always going to be 90 degrees, right? That's not like.
It really, I mean, when it would not be 90 degrees.
No. When it would be 90 if it's like gonna be normal to the fall, but if it wasn't, then it would have to be like close to or on top of kind of like the side of this, so you know.
Yes.
Sure.
So I think so. Can I erase this calculation? Is it clear for everyone? So I think what you're saying, George, is correct, but just make sure that don't leave anything. So let's say for this point, if we want to calculate the distance between this point and the entire plane, then that distance will always be the normal to that plane, right? So the shortest distance between this point and the entire plane is this one, right? And this is normal. That like this, the angle between this one and this and the plane itself is 90 degrees. But this projection point lives outside of the rupture itself. So in that case, the closest point, the closest distance between this rupture and that point, considering the finite dimensions of the rupture, is the distance between the top of the rupture and that point, right? In which case, it's not normal anymore.
Understood.
So if the projection point lies within the rupture plane, then that has to be normal. And in the cases that the projection doesn't lie within the rupture plane, it's somewhere along the edge, and it's the closest point between the perimeter of the rupture and the point itself. Is this clear for everyone else? And I think a lot of you also struggled with RJB. So what's the definition of the joiner and bore distance? Anyone? It's the distance between what? One has to be the side. The other is
Onto.
the projection of the fault on the surface. Correct. So that's the correct definition. And this dashed line, together with the blue line, which is the projection of the trace, defines the projection of the fault on the surface. So what is the RJB distance for this point?
Zero.
Zero, because it's inside the rupture plane. What is the distance for this point, side 2? Two kilometers, right? This line is 15, this point is at 17, so 17 minus 15 is 2. And the last one? The distance between this point and the project and
The dotted.
the dotted line, yes.
Is, or am I thinking, oh wait.
Just tell me, like, you don't need to give me a number, but what should be the line that we want to measure its length? As we said, it starts from the side, it connects this point with which point on the rupture?
The top of the, like, the surface projection.
This one?
No, I was going to the, where the dotted line was, but.
You
Oh,
mean-
I see what you're saying. Okay, so. So for that one, the RJB would be to. Almost like that one.
Correct. This one. And so again, the delta x is 2, the delta y is 2, so it's square root of 2 times 2. And one last question to make sure that we understand these distances correctly. Like if instead of having this gray line as the rupture, if we had the rupture being, let's say, this one, how would the RJB distance change?
It shouldn't,
And why wouldn't change?
because the horizontal projection is the same.
Exactly. So if you were to take either this plane and project on the surface or this one, like you look from top down, you will see that it covers the same area. Great. Any other questions on the distances? Okay, so let's do then the last one and then go to common. I thought this was clear, so I was able to tell guys that another strategy. Before we analytically first solve it. So I don't know if it was like sort of you were running out of time, but like, can someone tell me, like, if you have hazard curves from multiple faults, can those hazard curves intersect each other, or do they need to stay like sub-parallel? Like, is it possible to have a case that looks like this? Or no? Okay.
Um,
Yes. Is there?
You have a class here, right?
Correct.
Until,
Until 11, no, 10:50?
10:50.
10:50.
okay. I think this room is also reserved for the SACE tours that start at 10:05.
Oh, really? Because
Yeah, it's
Jackie
like
asked.
weekly event.
Yeah.
I don't know.
I
Is it
asked
okay to move to 133?
for us.
Uh-huh, Is that
Why
okay?
is 133?
yeah,
The conference room?
uh-huh.
We
Is that
could-
okay, or?
Yes,
Because the tour, usually we have like 30 guests and 133 will be
Okay,
small for,
I see. I asked Jackie and she told me to come here because the other class that we were in had like issues with the microphone. But we can move there.
apologize for that.
No,
Yeah.
no worries.
Yeah, we have already reserved this since last semester. Again, it's like
Okay.
tours for the high school kids and parents to explore different.
We
engineering programs.
will finish this and then we will move to the
Okay,
conference
okay,
room.
I will open the door. So
Yes,
that
would you please check with Jackie that then no one will come to that room to kick us out as well?
Okay, sure,
Thank
yeah.
you so much. So, yes, this is a possible solution. What would this, like if this is fault 1 and fault 2, what can you tell about fault 1 and fault 2? 1. And this is fault.
Fault one has a higher probability of having like lower ground shading at the site, and fault two has a higher probability of more.
Yes, so when would that happen?
Oh, when, um,
What is required to have a lot of scenarios that create like a lot but with ground motions?
higher,
Higher activity rate. And in plain words, what that means?
there's more reflection.
More, yes. Independent of magnitude, because the activity rate is the number of events above magnitude 5. So yes, so this one has a high activity rate. And the value of the activity rate is the value of the origin, close to the value of the origin. And the other you said has more events that are contributing to stronger ground motion. So what would that mean mathematically?
It is a lower activity rate, like a higher chance of having it.
What would be the difference between, like, let's now have like, I don't know, a third case. That looked like this. What would be the difference between this orange and this black line? The frequency of that earthquake happening is the same, but what is different?
So probability of a larger. Is that correct?
The probability of a large ground motion, and what would affect the probability of the large ground motion?
That's the,
like we have P of SA. P of SA greater than Z is what? 1 minus P of ln of SA minus mu divided by sigma, right? So really changing the sigma doesn't going to change this number much. What is going to change this probability is changing the mean. So this is a scenario with a larger median or in log space mean ground motion compared to this one. Is this clear for everyone? Okay. Maybe let's move to the other conference room and then continue.
I think there we can record.
Hmm?
There we can record the session.
Yes.
So maybe we can move back to that classroom.
To the original at Jarvis. We can.
Yeah.
Which one do you prefer, Jarvis or the conference room?
If we are in Jarvis, then we can record it.
I believe in both cases we can record it.
Oh, then it's fine.
Okay.
Apologize for that. Yeah. I think there is a double booking issue in song. And I talked with Jackie and she said it's okay to use Cata 136. And I opened the door already. And we can resolve the conflict of schedule maybe later.
Yes.
Yeah.
Thank you.
Yeah, there is a weekly SACE tour for the high school kids and parents to be here. And you'll see engineering program. So the same time, 5 2. It's just 10 or 15 minutes, but it's a big time.
Yeah.
Okay, sorry for that.
No,
Yeah,
no.
apologize. Yeah, if it's small group, I'm gonna use Cat
Are you able to hear us? Okay. Let's go through this problem very quickly. Let's focus on that. So is it clear what would shift the hazard curve vertically versus horizontally? What would be there? Yes. The median would shift the hazard curve in which direction? Horizontally. And what will shift it vertically? Activity. Correct. Okay. So again, we'll click to the part one. So for fault one, how would we calculate the hazard curve?
First one would be the rate on the vertical axis,
Okay. So and that will be what value?
0.02.
0.02. So 2 to the power of -3, correct? And that will be here. What other points can we easily calculate? Where would that median be?
The rate times 0.5.
Okay. That will be 0.001. Yes. And the x value?
0.3.
Yes. So 0.3 is here and 0.001 is here, correct? Everyone agrees? And what will be a last point?
Epsilon 2.
Epsilon. What will be the epsilon for the point that we just drew?
0.
Epsilon of 0. So instead of going to epsilon of 2, can we go to epsilon of 1?
1.
Okay. What will be the spectral acceleration value for an epsilon of 1?
Zero. Not think about that.
Which axis are you thinking? The x or the y?
Well, that's fine.
Okay, median and so we have SA of epsilon of 1 is median.
Exponential. Exponential.
And
Sigma.
sigma. Okay. So here epsilon is 1. So it's median times exponential of sigma. I think we already seen exponential of 0.5, how much it is. 0.7, sorry, not 0.5, which is of standard deviation, is about 2. So it's twice the median. Right? So if 0.3 is the median, what is the spectral acceleration for epsilon of 1?
6.
0.6, correct. So this point 3.4.5.6, and what is the y value? What is the equation first? Of epsilon of 1 is ln 1 before that. How often can this ground motion happen? Could you please repeat? LNC. Okay, so lambda times
Times twice the mean.
times twice the mean. Why twice the mean?
Right. As you said, structural acceleration at epsilon is equal to 1 is equal to mean times the exponent of epsilon times standard deviation.
Yes, so that's for the x value.
Oh, that's for the x value. For the y value,
Look at the units, guys. This is units of spectral acceleration. So, like, and this is in units of 1 over here. Like, this thing has to be in units of 1 over here. What is this, or what is the units of lambda? 1 over here. So what does it tell us for the things that is missing? What should it be?
it should be a structural acceleration. It should be something in G's.
If it's something in G's times 1 over here, what would these units need to be? This here, which doesn't make sense, right? What is like G per units of here? What does a hazard get tells us?
It tells us the hazard given a certain plan.
Okay, what is hazard?
In this case, it's ground motion, structural acceleration.
Okay, it tells us for a given ground motion, what does it tell us?
How often it
That would have been a probability. Anyone else? It's really fundamental. So again, like David, it's fine not to learn everything, but some very fundamental things. I think it's important that we are all have a grasp on them. What does this like? Let's say that we draw this curve. This one. This thing. What will it tell us for a spectral acceleration of 1g? So for a spectral acceleration of 1g, our hazard is this much, right? It's, let's say, 10 to the minus 4, slightly higher than 10 to the minus 4, 1 over here. What does this mean?
that means that you may experience a ground motion of 1g every 10,000 years. Visitors.
Exactly. A ground motion that is equal or exceeds 1g. Right?
Yes.
And the 10,000 years, how did you calculate it? You took the 1 to 10 of 10 to the power of minus 4 and you took the reciprocal of that, right?
Yes.
So that also tells us that if you were to count how many times you will have an acceleration that will exceed this spectral acceleration within 1 year, how many times would that be? In 1 year, you will see this ground motion 10 to the power of minus 4 times, right?
Yes.
So then if you wait for 10,000 years instead of 1, so you multiply the number of times that you're going to see it within 1 year times the entire period, 10 to the power of 4, then you will get 1 ground motion per 10,000 years.
Yes.
Is this making sense for everyone?
That makes sense.
Okay, so in that case, to calculate then the hazard for an arbitrary ground motion, we have how often an earthquake that is capable of producing that ground motion is going to happen. That's the activity rate. And then what is the thing that we are missing to calculate actually how often that ground motion is going to happen?
We're missing the probability of that ground motion happening,
Given that scenario.
given that's,
Okay, and this is the 1 minus phi,
yes.
right? Again, is this clear to everyone? Or right? So for an epsilon of 1, what is 1 minus phi? Probability of exceedance. What value it is? If epsilon is 1, then 1 minus phi of 1 is
Off the top of my head, I don't know. I can pull up Roland's paper that I have
Yeah.
the CEF on, but
0.16.
0 plus 16.
Okay, so
Yeah, I didn't know that value off the top of my head, I'm sorry.
it's a standard value, so that's it's kind of useful to remember.
Yeah, yeah.
So then to calculate the hazard for epsilon of 1, it will be lambda times 0.16. And this will be a point somewhere here, let's say. Right? And then you're going to repeat the same thing for the second case. So again we will run out of time and we will not go through the homework. So how would the hazard curve for the second fault look like? Very quickly.
Starting at 0.08.
Okay, so it has a higher activity rate. We'll start above the hazard curve for fault 1, right?
Yes.
So it will start here.
Very roughly, it'll have on the horizontal axis, it'll have a smaller, so closer like to the left, I guess.
Why would that be the case?
Because it is lower mean value.
Exactly. So at point 15, what will be its value?
It'll be equal to
What's the probability of exceeding the median?
probability of exceeding the median is, isn't it this? Oh, it's the same thing as the other one, so
Yeah.
twice 0.07. I mean, twice the mean, excuse me, twice the.
No, twice.
Okay.
That's the spectral acceleration for the epsilon of 1. Again, spectral acceleration x-axis, hazard y-axis. So we are now calculating the hazard for the median. So we know the value for the spectral acceleration. The value for the spectral acceleration is 0.15. So we are on this line, right?
Got it.
What y value?
50%.
50% of 0.08. So 0.004, right? Here. And so it will be something that will look like this. Is this clear to everyone? motion. Any questions maybe, or especially from I think also online. Are they still online, Sabah?
Yes.
Like the people, especially who struggle with this problem, is it clear for them or okay? That's...
Voting all thumbs up.
This one, yes, that's much more clear. Thank you. Now let's move to what we were thinking to do. So homework 2. I think all of you were able to calculate the probabilities for the density for the magnitude correctly and then calculate the probabilities. So I'm assuming that will be, we will not spend time on that and we will go through the remaining of the questions. So, and if you want to pull up your spreadsheets as well, you do so. So I think all of you were able to easily calculate part A, part B, part C, and now we are in part D. Okay. Sorry. Using the ground motion model given, compute the median and the sigma for 0.2 and 2 seconds for each scenario. What do we do for this one? Any volunteer to do the 0.2 seconds? Chris? No? Why? You're not sure what we need to do?
It's an acronym at a period of 0.2 seconds.
Hmm?
So I want to see what I have. So
Can you zoom it in a little bit more?
Yeah.
Yeah.
We just need to calculate the median. How do we calculate the median? So what does the ground motion model gives us? And what else?
sigma.
Sigma. Okay, that's the goal. That's the purpose of a ground motion model, to give us the distribution of a ground motion given a scenario. So we already have all of the information for the scenario. So we know the magnitude, we know the distance, we know the top of rupture, we know the VS30. So we just need to program that equation here. Who can do it? Okay, please come here and code the equation for us.
Question.
Yeah, in the question.
I'm not familiar with Maple.
Okay, what would you like to do? Keep what you were saying.
We need to
Write this equation, yes.
and see if she's
The table.
yeah.
The table is. Yes, the table. You want to copy it to the other spreadsheet?
Oh god, okay, that makes a lot more sense.
So maybe it's not
Okay. You just need to place it more, that's the only difference between some bugs.
Yeah, I think I got confused looking at where all those like smaller numbers came from when I was looking at my
With smaller numbers?
like the 0.059, the 1 point whatever. Because I was looking at like my Excel file
Mm.
and I was like, where did all this stuff come from? For a second there.
What button do you do to automatically lock this cell when you type it in at full? Or, okay, thank you.
And if someone had issues with this part of the calculation, please update your calculations as well. Is this number correct? Consistent with what the rest of you calculated? And you also calculate the sigma. Thank you. Do we all agree with these numbers?
Could you go back to that first formula?
We're not much.
Yeah, this. But sigma is fine. Are you matching something?
Minus 2.2.
Yeah. Yeah, good things. Well, I think so for the third term there is a minus there. They put at B7, I think. No, move to the left.
Yeah,
Yeah, I think there is a minus there.
instead of plus. Why?
Oh, okay, the coefficient. Oh, there is
Did you use natural logs or log based then?
not sure.
Okay. 4.6 times R up plus sector.
Let's see.
Okay. Can you press enter now? Is this a number that you got or still it's different?
Yeah, I redid mine, I got negative 2.17.
Okay.
Is that where everyone's at or am I? Okay. And then the following one first switch to the negative 0.05. Where is that?
Still different.
66.
Zif 5 plus 6 times 5 magnitude. The distance is correct, it's 8 kilometers, or did we mess something up? Okay. I think it's this one. This one should not be G5, this should be CH5. Yes. Okay. Okay, thank you. Okay, so thank you. Who now can calculate? So let's assume that you also have done this for 0.2 seconds because it's the exact same process. So now question is, for the following Z values, these are all the Z values that are given. Plot the hazard plot the hazard for each source and the total hazard. And I think that's makes you went like a lot of you struggled and then the rest didn't make any sense. So there is an intermediate step that it's assumed that you know what to do. What should like to calculate the hazard? What do we first need to calculate? Anyone? The activity rate, we already have it here, right?
Oh, okay.
Yes, so yes, the activity rate and,
The probability of exceedance.
okay, for all of these values, right?
Yeah.
Okay. So who can calculate here the probability of exceedance for 0.01 seconds for all of the sources? Any volunteers? You really want? Yes, please. You want? Thank you. Okay, this will be the, yeah, here. Okay, and now also to be easy to drag them, what you can put like a dollar sign.
Oh, okay.
Yeah. Two, three. And I think you also need a dollar sign for Q3, right? So that you don't drag on Q, on 3. So if you drag it down, it doesn't move. Is this clear?
Yeah, I think after going through the like thing we did on the exam, it makes a lot more sense now.
Okay. Okay, now we have this. We still, what else do we need to do to calculate the hazard for all the different scenarios? I think if you just select the entire row, then click.
Not familiar with that.
Okay. So this is the probability. How can we now? What else do we need to do to calculate the hazard? Unless who else wants to continue? Chris, your turn. Give it a go.
I got up to that step, but
It's okay. Let's see if we can help you move past this point. Thank you. Or George, do you want to give it a go? What else do we need, guys? We have so we need to calculate what is the equation for the hazard that we need to calculate. Okay, please. This, yeah, call it hazard. So, okay. So
we already have the probability and we have the, if I'm not mistaken, we also have the activity rate.
yes,
So then all we need to do here is multiply what we have
with the activity rate,
with activity. Is that correct or am I misunderstanding?
there is something that is missing. What is missing? What was different between the problem in the midterm and this problem? Yeah, I can answer that. The difference is in the midterm, each fault was producing a single earthquake at one particular distance. So the activity rate was the activity rate for that specific scenario because there was no other scenario.
So then I'm assuming there's a way to have the activity rate change with the givens.
Correct. So we have the activity rate of the fault. That's what you have already calculated when you are balancing the moments here. And now we want to go from how often an event on that particular fault is happening to what is the rate that specific scenario happening. So here, let's say for source one, which is again one, which only produces one event, what is the probability, what is the rate of that particular source happening? What will be the thing that we need to consider? Is the question clear or the hint clear or is it still confusing?
I think I'm confused about because source one is just has one type of earthquake event can happen. So
Yes.
wouldn't that just be the
That will be correct.
that would be correct for the first
First
one.
one. Okay. For the second one,
For the second one,
will be this number,
Mhm.
this number
Yeah.
times what?
times what is this red column? What is that again?
That's the probability for the magnitude. So the probability of that magnitude event happening.
So then would it make sense to multiply the rate by the probability of that magnitude?
Happening, yes. Anything else that we need to multiply it also with?
And we also calculated the probability of the location.
Yes.
So kind of a combination between those things. So it would be the probability of location times the probability of that magnitude times the activity rate.
Correct.
Then you're multiplying that by the
Probability of existence of the ground
Yes.
motion.
yes.
Yeah. So can we do that calculation?
We're gonna see if we go, everyone will be confused on how to use the Mac today. How to do that? Let's see.
Okay. Okay. We can continue. You are correct. You are doing the first row. This and this and this and times this. Great. And now if you also want to put dollar signs to make sure that when you drag it, where did it go? Can you change the color maybe? Okay, great. And put dollar, what do we need to fix? We need to fix the activity rate. So there should be a dollar sign in front of J and 2.
The dollar sign.
And in front of 2. So we need to fix.
Yeah.
Okay, great. And then for J5, K5, and L5, you want to fix the letter.
So it's just there.
Okay. This one you don't want to fix it because that changes for every ground motion value. So you
not Q.
yeah. Okay, so now you can drag it horizontally. And now if you drag for the next one vertically, like it once, I think we need to change the activity rate here. So if you click here, instead of J2, it needs to be, can you go to that back? It needs to be J2. Yeah.
You guys do that like thing, you just click down the whole column.
Yes. So, but it's not the entire column, it's for all scenarios too. Because when we go to scenario 3, okay. Now let's, since we're running out of time, what is it asking? Calculate the hazard for each source and the total hazard. How do we calculate the hazard for each source?
We are gonna plot.
What we have just calculated.
You just calculated the hazard at a given
Ground motion.
motion.
For each,
For each magnitude. So I think what we're gonna do now is we can. If I'm understanding this correctly, we plot it from. Two.
no. The hazard curve is again spectral acceleration versus the value of hazard. These are the different magnitudes and the different locations for a given source, right? So wouldn't the total hazard for that source be the sum of the hazard from all the possible magnitudes and locations that are part of that source?
Yeah, that makes sense.
So then we would need to sum all of these. Okay, can we do that then? There is a question. Can you read it, please?
You're saying we should also multiply by the probability of location. I like it.
We have already done that. Here. This is the activity rate, the first number, and the second is the probability of magnitude. The third is the probability of log of y, and then this is the location along there. Okay, so let's calculate the hazard for each source. What is the hazard for source 1?
So for source one would just be. That would just be that. And then
Yes.
like we plot it as that would be the first drugs. So
And we plot that against which values on the x-axis?
these.
Okay,
These would be the
correct.
values on the x-axis. These would be the values on the y-axis.
Yeah.
Yeah.
Or maybe let's say, let's keep all of them. So let's say fault 1 or fault 2 and then background. Okay. And we said this is fault 1. Right? And we calculate follow through. Okay.
Does anyone know where fault two ends number was?
I think it's changed from spreadsheet to spreadsheet, so you need to. I can calculate.
Yeah.
We're on 400.
400 something?
Yeah, 400.
We are fixing. Should be some. I will do it very quickly for you.
I appreciate that.
So we start from here. Here, right? You agree? Okay, and then we are also again with some all of these values, and then for the background, what would we do?
We'd sum the rest. So anyways that aren't related to source.
Okay, so we start from here
And
down to the bottom. Here. Okay. These ones, and we have that the ground motion values are these values, correct?
Mhm.
Okay. Now we take this. We take this one. This. It's this one, and it's create a plot, and then we put this in log scale. So logarithmic x, logarithmic y, and this is our hazard for each source. And if you want to calculate the total hazard very quickly,
we'd sum at each ground motion. So we'd sum for
yes,
one in there.
correct. I think a lot of you ended up summing, like, and I don't know why, but summed across ground motion values, the different hazard instead of for one given ground motion, all possible contributions. And it's important to recognize that the hazard is for a specific ground motion, so you cannot sum across columns, you need to sum across rows. Is this making more sense?
Yeah.
Okay. That's it then for today. Next time, I already posted the third assignment, so if you can look at it, and then we can go through what is needed. So for that, we'll use the software that we saw. And then I think we'll have one more lecture on hazard, and after that, we can talk about dynamic solid properties and site response. Yeah, thank you everyone.